So we agree that transition metals have variable oxidation states. They form complex ions. Now the next property to talk about is they form colored complexes. Why is this phenomena? A transition metal, when it's isolated, when there is no ligand in proximity, has d orbitals that are in the same energy level. So d orbitals, you have 5 of them. When there is no ligand in proximity, they are all in the same energy and there is no color to talk about. But when a ligand approaches them, d orbitals are placeholder for electrons. They are negative spaces, and ligands have negative electrons. They repel each other and they form 2 distinct energy levels. 3 of the d orbitals stay down here and 2 will move up, and there is a change in energy delta E, and therefore the phenomena of color comes to life. Now the second attribute or requirement is that you have partially d electrons. If it's completely filled, there is no color. If it's empty, there is no color. Now let's look at one example. Why titanium 3 plus is purple? If you look at titanium, its electron configuration is argon 4s2 3d2. Now when it forms a charged titanium 3 plus, it will lose its 4s completely, and 3d will have 1 electron left in it. So there is possibility of color. Now in isolations, this is what happens. So when it's isolated, we have 1, 2, 3, 4, 5 d orbitals, same energy level. Now white light comes through, and white light is mixture of Roy G. Beeve, all the colors. So when we put it next to a ligand, this is what happens. It will split into 2. The electron's still down here, so this is when a ligand has approached. Now white light in this form is going to go through, but what happens is there is a transmission of the electron. This electron is going to go up here, gets excited, goes up here. So this is the excited version. And what comes out is a color in form of just blue, indigo, and violet left, and this is purple. And there is a complementary color. Depending on what you absorb, the leftover of the color is the color that you actually see. So in this case, you are probably going to see this area because the rest was absorbed. So this is absorbed, this is being reflected or transmitted. Now the color depends on four properties that you need to be able to argue. One is the identity of the central metal ion. If you look at this example of chromium versus iron, you see that chromium is different from iron, therefore the color is also different. The other one is the splitting power of the ligands, and there is a spectrochemical series. For example, as you go next to cyanide, has the biggest split, biggest power, and while iodine or iodide doesn't have as much. If you look at this example of cobalt, for example, chlorine is not splitting as much the D versus ammonia, which is splitting a whole lot. The other one is just oxidation number. If I give you a complex of Fe2+, it's green. And if I give you a complex of Fe3+, it's red. So depending on what's your oxidation number. Finally, it's the shape of the complex ion. The more ligands you have, the deeper the color that you see. So, and that's your last argument. Is it octahedral or tetrahedral?